This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Everyone has one handout? No? Anyone has some leftovers at their end? Pass it all up. Thank you. Okay, good morning, everyone. Let me start. Right? Yeah, we are recorded. So this handout that I'm passing is a kind of quick review of what we've done last week. Okay, just so that you have it handy in case you are wondering during today's lecture, this lecture, what is this matrix, what is that matrix? We are going to practice rotation matrices kind of during this lecture, okay? Now, if you remember, at the very first lecture, I gave you Newton-Euler equations, and there was some R or R dot, R double dot inside. So today we are preparing the idea of position vectors, okay? So in order to set up Newton-Euler equations, we would need to start solving problems. First, putting in some coordinate systems, then evaluating or finding out rotation matrices, then finding position vectors, which we are doing now, okay, and then taking derivatives to find velocities, accelerations, all right? We will do the velocities, accelerations later. Today we are doing just position vectors, and in the next lecture, angular velocities, okay? So what we are going to see is 4 examples, okay? It will be quite dense lecture, so be with me, please. The first 2 examples are quite straightforward. The second 2 examples are a little bit more challenging for first-time dynamics students, all right? And please stop me if you have any questions, okay? Don't lose me. Do stop me. So the first example is in the plane, just 2D. We will rarely have these, but sometimes. So what you see here is 2 links, okay? Link 1, link 2. They both have length L, and 2 angles, alpha and beta, and notice their direction of growth. These angles describe the configuration of these 2 links, all right? Now, what is required here to find the vector going from this point A to this point C, okay, this vector from A to C, and to represent this vector in frame 0, that is in the coordinate system that is shown here, okay? Now, can you do it without fancy rotation matrices? Definitely. But what I want to illustrate is how to use what we've learned, okay, just in general, and then we can move on to more complicated examples that you will really struggle to do without rotation matrices, all right? Yeah, so just keep in mind, we are trying to find this vector from A to C. It will depend potentially on these alpha and beta, And we can find this vector in any coordinate system that we want. Okay? In this question, we are asked to find in a particular coordinate system, 0, this black one. But in general, if I don't ask you to represent a vector in a specific coordinate system, you're free to assign and choose to assign whatever coordinate system you want and represent any vector in that coordinate system, all right? So the way to go in general, you will see this rectangle here. This is what we will apply for each of the 4 examples in this lecture. So the first thing would be to assign or allocate coordinate systems in a convenient way to work with. Okay, so the first thing is just to stick axes onto this figure. Okay, and then determine rotation matrices. So let's say we would stick a coordinate system that would be attached to link AB and another one that will be attached to link BC. Okay, so let's say we define these coordinate systems or label them as 1 and 2. We would like to find rotation matrices between 2 and 1, 1 and 0. Okay, this is the second step. And the final step would be to find the vector that we are aiming to find. Okay, now actually how to find a vector. In order to go from A to C, we will normally follow links. Okay, we will sum vectors, the vector summation way. Okay, so in this case, we will go from A to B plus a vector from B to C. Okay, that would give the vector from A to C. Right? You're familiar with vector summations, I assume. Okay, so this step is assigning coordinate systems. So you can see the red and the blue one here. The red one is attached, like glued, to link 1, that link AB. And the blue coordinate system is attached to link BC. What do I mean by attached? As the link is moving or changing its orientation, the coordinate system is moving along, moving with it. Okay, now I am giving you some rules of thumb how to attach such coordinate systems yourselves. Okay, so tip number 1 is to try to have one axis going along a link. Okay, now another tip is to have one axis going along the joint about which the link is rotating. So in this case, axes Z1 and Z2 are parallel to the joint axis. Okay, if you think about it, the joint axis for these links. Okay, this is not written, but maybe you can write it for yourselves. And these tips are not mandatory. Okay, you will manage without them as well, because some links are not straight like that. Some links have weird shape. So you will not always be able to apply this tip. And the other tip is try to have some commonly used, these 1 out of 6 that I gave you, commonly used rotation matrices. In this case, you can see if I would copy this blue one on the red one, if I would kind of join their origins, then you will see that frame 2 is doing a positive rotation about Z1 by angle beta. Okay? So frame 2 relative to frame 1 is just like what you have in the handout. On the top right side, on the top, just on the plane. And similarly, the red coordinate system relative to the black one is doing the same. Positive rotation about z. Okay? Sorry, I forgot. This is about x. So the bottom one, right? The bottom one on the right is the z rotation. Okay, so we will, in this case, obtain common rotation matrices. And the next step is to find the rotation matrices that match my assignment of frames. All right? Now you need to be, so there is a mixture of flexibility. You could have assigned frames 1 and 2 in a different way, but I have assigned frame 0 for you. Okay, so in the exam, for example, if you come up with your own frames, that's fine. But if I give you one, if you are doing a rotation matrix between, say, frame 1 and 0, it has to make sense for all the future derivations you're going to do. Okay, so just keep in mind what is given. All right, so these rotation matrices, from 1 to 0, from 2 to 1, both of them are of this kind of class or title, positive rotation about z. Okay, one is by angle alpha, the other one is by angle beta. Okay, now this is crucial that you understand until this point. Are there any questions? No? Okay, so the next step would be to go from this A to C. Okay, and what we are going to do is follow this path from A to B and from B to C. Okay, we are going to sum these vectors. Why are we doing this path? Because now going from A to B is simple in the red coordinate system. Okay? Any colorblind people? Don't tell me. I get them from time to time. I will need to adjust the exam for you. But in general, if you're not colorblind, I'll be using a lot of colors. So red coordinate system is having its x aligned with link AB. So the vector from A to B represented in frame 1 will simply be L00. Okay, so it's easy to determine. Okay, and similarly from B to C, because BC is aligned with, say, the negative x2, yeah, it will also be easy. What will be the vector from B to C in frame 2? Minus L00, right? Okay, so what we are doing here is now finding this RAC, yeah, as the sum of RAB and RBC, okay, vector summation. And because I'm asked to find it in frame 0, I need the result to be in frame 0, but I'm doing a gradual summation. So first, as I said, RAB I'm finding in frame 1. Then I'm using the rotation matrix from 1 to 0 to make this combination in frame 0, like this one. And then RBC in frame 2, all right, as I said, minus L00. And then I'm rotating it, okay, quote unquote, to frame 0 by multiplying it, pre-multiplying it by the rotation matrices, okay, from 2 to 0. How to do that? From 2 to 1, from 1 to 0. Okay, and I'll be using these two rotation matrices. Okay, hopefully it's clear. Okay, so this is some matrix multiplications, right? And if you do all the substitutions, this is what you get. Okay, so maybe check that it makes sense. Okay, I'll stop for a few seconds. if you need to digest. And by the way, there is this multiplication of two matrices. Both of them, because both rotations were positive about Z, so both of them are of the same type. Yeah. So it's like rotation about Z by alpha, and then a bit more by beta. So overall, if you multiply them, yeah, you will get this combined one if you're using some trigonometric identities of adding or subtracting angles. Yeah, so say the first component would be cosine alpha, cosine beta, and then minus sine alpha, sine beta, plus 0. So that would correspond to cosine alpha plus beta. Okay, so that makes sense. You don't need to really calculate it. You can use this property straight away. Okay, so this is how you go. Okay, and this is the final result. And this is the most simple example I can give you. Okay, and I'm just saying you will need to use MATLAB for a bit more complicated examples. Okay, for matrix multiplications like that. Any questions, guys? Okay, ready for the next example? Okay, so here we have a three-dimensional system with two links, okay, the vertical one and then a kind of wing that can go up and down. Okay, so it can rotate like that. And in this drawing, the specific angle alpha is not, it's not perfectly defined here, because when alpha is 0, you don't know exactly how the system is oriented. So this is not a full definition. In the next slide, it will be the full definition. So maybe imagine here, when alpha is 0, that link, that wing at the top is facing you. Okay, so outside of the slide when alpha is 0. Okay, I think. And where is y 0? Inside, right? Because you go from z to x, your thumb is inside. Okay? So remember that. And what you are required to find is the vector going from O to C. Okay, so this vector from O to C, and you need to represent it in frame 0, so this black frame. Okay, similar thing. Okay, now what we are going to do is, again, attach coordinate systems. All right, first I feed you with my choice, then later you will be doing your own choices. Determine rotation matrices according to that choice, and then finally doing the algebra. Okay, so I would be, so how do I attach the coordinate systems? Here is a drawing of the top view of this system. So you don't see the vertical link, you just see the wing from top, from above. Okay, so y0 was going in to the page in the previous slide, right? And I said when alpha is 0, that wing is facing you. Okay, so when alpha is 0, the wing is pointing on the opposite direction of y0. Okay, so this is what is happening with this alpha. I'm attaching frame number 1, the red one, to essentially this rotating vertical link. Okay, such that y1 will always be pointing away from this wing, and x1 will always be pointing along the joint axis. Okay, so frame 1 is just doing this. Okay, if my right hand is x1, y1 is my left hand, and my head is Z1. Okay, it is doing this. That's why we need the video. That's the video. Okay, frame 2. By the way, what type of rotation is frame 1 relative to 0? Positive rotation about Z or Z0, yeah. Okay, now here I'm attaching frame 2. Also, according to these guidelines, okay, I'm having my Z2 axis along the wing, or just pointing the other direction, okay, and my X2, which is not drawn, X2 is along the joint axis, okay, which will be convenient. So something to do with X2 is the rotation, the axis of rotation. And the rotation is by beta, but if maybe think about that for a second. Here, where is X1? Pointing in, right? And X2 also pointing in, right? And the beta, if you follow with your fingers around with the beta, your thumb is pointing out, right? So in the opposite direction of the x's, right? So what type of rotation is this, or what type of rotation matrix you'll get? Negative x, yeah, negative x rotation, yeah. So you can prepare your rotation matrices like that. The one between 1 and 0, so rotation matrix from frame 1 to frame 0 is this positive rotation about Z, and this one from 2 to 1 is negative rotation about X. Okay? Does it make sense so far? Any questions? Okay, no questions. Then what is the vector from O to C? From O to C, ROC, in frame 2. Right, 0, 0 minus L, because I need to go L units in the negative Z2 direction, right? And that one is easy, and this is the idea behind why I assign coordinate systems in the first place. So what I will need to do to find this vector ROC in frame 0 is just to rotate this ROC in frame 2, from 2 to 1, then from 1 to 0, right? And then I get my result. So, okay, so this is, as you said, 0, 0 minus L. Okay, and then I need to pre-multiply it by these rotation matrices to get the desired result. Okay, so the full calculation is here. All right. Any questions again? Okay. So example number 3, right? We are required to find the vector going from this point A at the center of this T-shaped bar. So from A to point D, which is here on the perimeter of the wheel. Okay. Now this drawing is not fully defined, so maybe write down what I'm saying to you now. Okay. When the angle gamma here is 0, point D is touching that platform here. So D, this point D would be the bottommost point on the wheel when gamma is 0. Okay? Otherwise, gamma is not fully defined, or the configuration of the system is not fully defined. All right. Now, when gamma is not 0, this point D starts going away from that gray platform at the bottom, okay? And we need to find the vector going from A all the way to D, okay? In terms of vector summation, our strategy will be to go from A to B, from B to C, which is at the center of this wheel, and then from C to D. Okay, so we are summing these 3 vectors. But each of these vectors is conveniently represented on a different coordinate system. So we are going to attach 3 coordinate systems in a way. But actually one of them is already given to us, which is this black one, frame 1. And frame 1 is rotating together with this T-shaped bar. Okay? There is no frame 0 attached to anything here. And the question asks you to find this vector going from A to D, RAD, in this rotating frame 1. Okay? Which is fine. All right? So if you go from A to B, this is parallel to, well, opposite direction of x1. Okay, so convenient already. Okay, so what I'll be doing, I'll be attaching one coordinate system to this rod that is moving with this angle beta, and another one to the wheel. Okay, and I'm trying to follow the rules of thumb that I gave you. Okay, so this is how I attached the coordinate systems here. The red one is moving together with this rod BC. All right, so that the vector from B to C is 2r units in the negative x2 direction. Okay. And what kind of rotation do we have from this frame 2 to frame 1? Positive y. And positive about what? Yeah, so positive about z1. Okay, notice how when beta is 0, my x2 and y2 are aligned in their orientation with x1 and y1. Okay, so when beta is 0. When beta is growing, we are getting this rotation. Okay, if you follow the direction of rotation, or this direction of beta, your thumb is aligned with the z1 axis, right? So it's a positive z rotation. All right? And now so remember this axis here is x2. Okay, x2 is this way. And now this drawing is done. Yeah, this, if you are looking from here, okay, if you are looking kind of from above, normal to the wheel. Okay, so you are seeing this side of the wheel. Okay, and the axis that is coming out is your x2, the red one. Okay. And what I attach to the wheel is the purple frame 3. Okay, and frame 3 is rotating by gamma about the x2 two axes. Okay, so I just want to assign it like that, when gamma is 0, my frame 3 and 2 are co-oriented. All right, so when gamma is 0, I'm having the same orientation between the red and the purple frames. Okay, and the vector from C to D, how would you represent the vector from C to D in frame 3, in the purple frame 3? You're going in the opposite direction of Y3, okay? Yeah, 0 minus R, 0, right? So now we need to, well, first determine the rotation matrices. Okay, we have from 2 to 1 and from 3 to 2. This one is positive rotation about Z, and this one is positive rotation about X, okay, by beta, by gamma. All right? I'll pause here because I see that you're trying to follow. Any questions to this stage? Yeah? Yeah. If it's not clear, my apology. I don't want to crowd my slides too much. So it's something I mentioned, and I mentioned it, I think, here. So frame 1 attached to the T-bar. Okay, it's part of the wording of the question. Yeah. So in an exam, I'm actually specifying everything. So my questions are pretty long, but my slides not so much. So yeah. So it's my instruction. Frame 1 is attached to the rotating T-bar. Okay, frame 2 is attached to this rod. Frame 3 is attached to this wheel. Okay, by attached, I mean like glued onto. Okay, moving together. Any other questions? Yeah?
How do we know we rotate first around theta and then gamma and not gamma?
I don't physically rotate anything. Okay, maybe in the order of links here, I can delete the wheel, right? And I'm only left with this rod, right? And then there is no angle gamma. There is just the beta. Who asked? Sorry, I lost. Yeah. So beta happens first in the sense that as you're moving down from A to D, you are passing through a link that is rotating with the beta angle first. And then you are coming to a link, this wheel, that is rotating with angle gamma. Okay? But there isn't much first, second. Okay. Yeah? Sorry?
Should the direction for the matrix be reversed?
The direction inside here? The order?
Yes.
Maybe the labeling of the coordinate systems is 1 and 2. It doesn't matter. I could label them triangle and square. And then swap. It doesn't matter. So my labeling of 1 and 2 is quite arbitrary. All right? But what I have inside here matches exactly the drawn arrows. Yeah? Any other questions? Yep.
Okay, we see that frame 1 is attached to point A.
Not to a point, but to a whole body. Because the point can move, Ah, do you mean the origin?
No, the Y1, X1, the frame 1.
The entire frame, yeah.
Does it be attached?
Yeah, so it is attached to the entire T-shaped bar, okay? And the meaning of attached is having the same change of orientation. Now, a point has no orientation. I cannot define orientation for a point, right? But for the T-shaped bar, like if I'm the T-shaped bar, I can be like this or like this, right? I can have different orientations. So if this is frame number 1, when the T-shaped bar moves, the frame moves together with it, like that, right? And I don't have to stick its origin in any particular point, okay? It can be floating in space, frame 1, all right? So it doesn't matter, as long as the orientation is consistently the same. Okay, so I defined it for you. Frame 1 is attached to the T-shaped bar. Are you still puzzled? No? Right. Okay. So now finding the vector from A to D. Remember, we are summing 3 vectors from A to B, from B to C, from C to D. Okay? So this is it, right? A to B, B, C, C, D. Eventually, everything needs to be in frame 1, because this is the question. Okay, so I want to work for each of these vectors in a frame that is convenient for finding that specific vector, and then using rotation matrices to bring all of these vectors to frame 1. Okay, so this one is conveniently represented already in frame 1. So from A to B, as we mentioned, I'm going 2r units in the negative x1 direction. So that's why it's minus 2r, 0, 0. Okay? For the vector from B to C, I'm going 2r in the negative x2 direction. Right? So this vector is rbc in frame 2. And then I'm rotating it from 2 to 1 using the rotation matrix. Okay, and then finally from C to D, from the center of the wheel to this point D, I'm going r units in the negative y3 direction. Okay, and so this vector is r from C to D in frame 3, and then rotated from 3 to 2, from 2 to 1. Okay, so eventually all the vector summation here has to happen in the same frame. I cannot sum 2 vectors in different frames. I mean, it will be meaningless most of the time. Okay, so I just need to substitute in the rotation matrices that I prepared, okay, and evaluate the result. All right? Again, remember, MATLAB is your friend. All right? Unless you are really happy to do matrix multiplications, right? You will do some in the exam. Yeah? When the exam, yeah. So in the exam, every semester from 2015, same question. What happens in the exam? We don't have MATLAB. Up to, at most, 3 rotation matrices in series with a vector. Okay? But I want to mention that the most important thing is to write down until here. Okay, if you correctly write down until here, the rest is just algebra, right? So it is less important. Okay? Saying that, it is still full marks if you only get to the final stage. All right. Now, last example. We are good with time. Last example. We have this tilted wheel here. And the question wants you to find the vector from the center of the wheel, point O, until point C on the perimeter of the wheel, right? And this wheel is mounted on this shaft. So the wheel itself is normal to this part of the shaft. Okay, and this part is with an angle to this part of the shaft, and this angle is alpha. And just notice that alpha is a constant angle, okay? Nothing is rotating with alpha, okay? It's a constant tilt. Whereas beta defines rotation, okay? So beta is changing with time as this wheel is rolling. And beta is defined such, or let's say point C is defined such that when beta is 0, so the vector from O to C, when beta is 0, will be parallel to x0 if this shaft is not rotated yet. Okay, so we have the rotation of the shaft, and this rotation is defined here by omega, and omega is not an angle, it's a rate of change of that angle of the shafts. Okay, so the units are different. Let's say alpha, beta are in radians. This omega is in radians per second. All right, so in order to obtain the angle will be omega t, where t is the time passing from the moment where the configuration is like this, okay? So when t equals 0, the shaft is contained inside the y0, z0 plane. Okay, this is, sorry? When t equals 0, the shaft is entirely in the y0, z0 plane. Okay, and then onwards, it rotates with this omega t angle. Okay, and also notice the specific direction of this omega. You see this line here crossing the rod, so it defines the direction for you. Is the shaft rotating in the y0 or negative y0 direction? Negative, right? So the shaft is rotating about the negative y0 direction. All right. Now what about the rotation of the wheel? Is it about this direction? Let me call this 1. Or this direction, 2. 2, right? So just pay attention. What about this alpha? Is it about the axis coming in or out? Coming in, right? So at t equals 0, alpha happens in the opposite direction to this x. Okay? Okay, so this is how I assigned the frames for this problem. Now, we will use the same problems in the next lecture, so pay attention to the coordinate systems here, right? Okay, so the red frame 1, coordinate system 1, is attached to this shaft such that y1 is aligned with this part of the shaft, or let's say the horizontal part of the shaft. Okay, so y1 is aligned like that, and look at the rotation with this omega. We have our rotation by angle omega t in the negative y1 direction. Okay, or in this drawing, which is done from here, let's say if you're looking from this direction here, in this drawing, your y, where is your y? Y is inside, right? So you are having negative rotation about y. Okay, negative rotation about y0 by angle omega t. Okay, now the next coordinate system is this blue one, frame 2. And frame 2, pay attention, frame 2, despite it being drawn on the wheel, kind of, it's not attached to the wheel. It is still attached to the shaft. However, it is tilted by this angle alpha, tilted by the constant angle alpha, just for my convenience to go along this direction. I want to represent this direction. And this shift, this rotation about alpha, happens about the x1 axis, or actually the negative x1 axis. Okay, why x1, not x0? Because x1 remains oriented together with the shaft, okay? Follows the shaft, whereas x0 is stationary. All right, so look at this drawing here, okay? Try to see if you understand. Okay, so we have here a negative rotation by angle alpha about axis Z1, right? And this alpha is a constant, I remind you. Okay, so if I take the derivative of alpha with respect to time, I get 0. Okay, we will use it next lecture. Try to remember. And then finally, the green frame 3 is attached to the wheel. Okay, so frame 3 here, the label 3 goes together with the wheel. Okay, and this is rotation by beta about the negative y2 axis. Okay, so negative rotation by beta about y. Okay, and now what's the next step? Get the rotation matrices that correspond to my assignment of frames, right? And then go from O to C. When I go from O to C, what will be that vector? This is x3. So in frame 3, it will be just R00, right? And then I need to use the rotation matrices from 3 to 2, 2 to 1, 1 to 0. It will automatically simplify everything, all right? So these are the rotation matrices. All of them are negative, as I mentioned, all right? And finally, the calculation is here, all right? ROC is R00, okay, in frame 3, and then I cascade it to frame 0 by pre-multiplying with these rotation matrices. Any questions? 3 minutes for questions. So please review that for the coming afternoon session, or if you want to ask me now in my consultation, come to my office with me, all right? Thanks a lot. See you afternoon.
Just a quick question. Is there any reason you choose to align one of the axes on the reference frame sort of opposite as opposed to along? You know what I mean?
No,
So just custom?
Yeah, but it helps me have rotation matrices as one of the 6.
Yeah, no, I was just wondering why you chose, say, imagine you have a link like this, and often you have the X pointing that way as opposed to this way. That's just preference?
It's not my preference.
Okay.
practice along the that option.
Yeah, sure.
And see that instead of saying cosine alpha, you'll have to do something like cosine alpha plus 90.
Okay. Okay. Alright, thanks. I have
Yeah.
just...
Sorry guys, follow me.
Maybe after
You have a lecture now?
yeah.
Sorry, because if I do my presentation here,
and luckily I didn't do more also. So the paper which came last year